Okay, so next up is my colleague James Wetzel from Co-College, and James is going to tell us about the imaging capabilities of the RLT. Okay.
Thank you, John. Yeah, let's just get into it. So one of the cool things we have on our website, when you take images and the next day, you want to look at where you took images from. They're on the website. This is a planetarium. You can move around. You can hover on the objects that we took images of. Take a quick. There's a little thumbnail. You can see it. Make sure you got the images that you wanted. And just if there's an external user who likes to see what we're doing. So if you want to go to our website every now and then and just say, hey, what did they look at last night? Hopefully that'll be working again soon. Okay, so the macro consortium is pretty cool. We have this website where anybody in the world actually pretty much can go on here, make an observation request. It may or may not get taken, but we have this submission form. You can submit the target. It's pretty powerful. You can specify cadences. So you can say, I'm going to do this object every hour. I'm going to do this object every 10 minutes. I'm going to do this object every minute, whatever you want to do. Throw that in there. The exposure times, filters that you want to use. The images are then reduced automatically by our server and then published on the internet so that anybody, all of you, can go there now and see the images that we've taken since a long time ago, because all of the archive data is on there as well. So if you have a source you're interested in, you want to see what did it look like 10 years ago, we might have that in our database. So that is at macroconsortium.org/images. We also have an ops planner tool that allows students to put the target of interest they want into this tool, and the tool will recommend, based on the filter that you select, it'll recommend how much time you should expose the camera to that object for that given filter. So you don't have to guess as much about, oh, should I try 10 seconds or should I try 60 seconds? Or, you don't want to overexpose, you don't want to underexpose, you want it just right. So we have this cool tool that helps you calculate or estimate that answer. So the instrument that we use has been talked about already, but it's the CDK20 with this really nice camera on it, and then 2 filter wheels full of filters, and then a external water chiller, which keeps everything cool in the Arizona sun. So in the first filter wheel, we have the Sloan URISI images, or sorry, filters that you can use. We have the low and high resolution GRISM in that filter wheel, and then we have some narrowband filters available. And then in the other filter wheel, we have the RGB for pretty picture and just broadband image. There are lots of light get through those filters, so they're useful in some cases. This is that filter wheel. Bill just talked about how we 3D printed an extension so that we could fit these GRISMs in there, but the GRISMs are so small and compact, they're really amazing little things that fit in there. And then just the standard spectrum available for our different filters. And then the GRISMs that Bill mentioned are available for image observations, and just they're super powerful. We use them all the time. The camera that is on our telescope here is this Andor Icon 936L. It has a Peltier cooler in it, which is capable of 100-degree delta from ambient. So if it's 20 degrees in the room, it can operate at -80 without any external cooling. So it's an incredible camera. And we also have this water chiller, which keeps it at 5 degrees Celsius, because in Arizona, it does get up to 40 degrees Celsius sometimes. So we want to make sure our camera can operate at -80 Celsius for the darkest dark current we can get. This is the quantum efficiency of the camera. So it's this green line here. So it's really good, above 90% in that visible range, which is where we want to be. Now, this is a nice flat field image in the background where you can see kind of the structure of our sensor, and hopefully after calibration that goes away. But what this sensor can do, it has 2.9 root electrons per pixel read noise at -80 Celsius. So it's a very quiet read noise camera. We have a couple of options to read it out. This is the low speed, or whatever we call it. And then it has a dark current of 4.2 electrons per pixel per hour at -80 Celsius. So Will did this great analysis here that basically told us you got to operate at -80 Celsius if you can. The darkest dark current. So that's why we choose to operate at -80, which is about as cold as it can get. And so we get the best performance there. We have this really great night vision almost camera. So there's a challenge if you want to have a webcam watching your telescope at night. If you buy one of these low light cameras, they often have infrared LEDs on them to shine. But you don't want that shining up your camera, even though your eyes can't see it. These eyes can see it. So this is a really great camera that doesn't have infrared LEDs. I don't know how it works really, but it just gives us a great view of the telescope to make sure we're not pointed at the ground. Which sometimes it does do. Okay, so we have this picture here, which is going to be the subject of the next couple slides. So the performance of our system is really good. We're at 22 magnitude for our G, R, and I filters, and this plot here shows that our noise characteristics are really dictated by the site and the sky and the source that we're looking at. So our optical system is more capable than what the site allows. So if we moved this system to a different site with better seeing and things like that, then we might be able to improve these numbers, and we're not sure how much, but if you wanted to copy the system and you moved it to, the Atacama Desert or something like that, then you might have a little bit better numbers here with the same equipment that we have. So, and this is very standard equipment, very nice, accessible to everybody. Okay, so our calibration pipeline is interesting. You can see the aperture starfish pattern here in this image, which again, hopefully disappears after you calibrate the image. But the images are automatically taken by the system, they're automatically calibrated by the system, they're automatically dictated, or not dictated, but put onto the website for other people to use. Which makes it great for intro students to advanced students. So if you have advanced students, you want to make them calibrate the images themselves, you can do that. But if you have an intro class, you just want to get them used to taking pictures and doing some basic analysis, then we can provide fully calibrated images ready to go. The calibration steps for a normal CCD camera, we do the bias subtraction, dark frame subtraction, we divide out the flat frame. We also do a cosmic ray removal with Astro Scrappy, and then we add in the FITS header some seeing and ZP mag calculations, because some analysis relies on those numbers. We get our calibration images either using the sky, so if the evening permits and if somebody's available, then we'll occasionally run a sky flat program. Or we have this screen, which is off to the side of our telescope, and we have these lamps on the front. I think they're halogen lamps or something like that. And this is inside the observatory roof, so during the day, we can take calibration frames while the roof is closed. We publish both raw and reduced copies of every image. So if you don't like the calibration you get, you can do your own, or if you want to study the performance of the camera without calibration, you can. We have those images available. In the FITS header also includes the calibration files that were used to calibrate, so you could download the calibration images if there's something curious you want to study. And then every morning we send an email to the users about the images that were taken the previous night. So this is a typical night here. 224 images were taken, 7.7 hours of integration time. All these users, how many images per user, and how much time each user. So this is an example of, you've got a class with 20 students or something like that. You're going to see images like this every night for all the different schools. And it's just a really great tool that we all have access to. Okay, going forward, we'd like to develop a better signal to noise model. This is camera and filters and everything. We did an upgrade just a couple months ago. So we want to get a better idea of this new system, create a signal to noise model that we can update our ops planner tool so people can have a really good idea of how much exposure time they're going to need for a given target. And then we want to move to a database schema so that when you submit an image, everything right now is going into text files, and which is okay, and it works, but we want to have records of every image requested, every observation requested, and if an image doesn't get taken, we have an easy way to take it the next night, for example. But the main thing is that we want this data to be accessible to the whole world, that anybody can download. So we need a tool that allows users to search targets, search integration time, search filters, search days that images were taken, so you can see what's available on our entire database. Historically and going forward. So we want to develop that out. And then the main thing is that all of this integrates with PyScope. So anybody can copy what we're doing with their own telescope. You can even use just like a little solar telescope and hook it up and use the system. So we're trying to make this available to everybody. We also want to add server-side tools so that if you go to macroconsortium.org, you can just analyze the images right there using Carta, using Jupyter notebooks. This will just make it easy for students who don't have a lot of background, or computer labs who don't have a lot of background installing these specific tools, to allow students the ability to just analyze some data. So eventually there might be a school somewhere, in Chicago that decides they want to add, labs to their classwork, and they can just use our website and our images, and it'd be great. Okay, so that's our image pipeline. That's the imaging capabilities. Thank you for your time. And if you have any questions, reach out to us. And if you want to use our images, go to our website, download them. Thank you.